Okay, let's just go ahead and get started. We have a little bit of a smaller class today, it seems like, than usual. Maybe people are taking spring break a week early. I'm not sure. Just to remind you guys, your homework this week is due on Thursday. I think it was originally due Tuesday, but we pushed it back a couple days. It's due Thursday. And then the way the schedule has been set up, you have a homework due 2 weeks from that Thursday, because we have homework every 2 weeks. So your next homework's going to go out on Thursday, due 2 weeks from Thursday. In between, there's a week of spring break. So we've tried to make the homework not too killer, because we don't want you guys to spend your entire spring break on your convex homework. But because you have 2 weeks of, for each homework unit, that's the way this one worked out. We can't really push that back any later either, considering what comes up afterwards, because the midterm comes up after that. We want to give you some time between that homework and the midterm. Any questions before we start today about homeworks, projects, any of the stuff to come? Yeah? Yes, yeah. So we're going to talk about Newton's method and then the barrier method on Wednesday this week. The week after, Javier is going to teach primal dual interior point method, and the homework's not going to be on that. So you won't have to worry about that. Otherwise, it would have been too short of a time period. Other questions? Okay. So this is the start of our second order methods unit. And we're going to talk about Newton's method, like I said, and then what we would call interior point methods, and we'll spend a few lectures on those. So the last thing we left off on was out of our duality and ophthalmology unit was called duality correspondences and uses. And just to recap what that meant, we defined the conjugate of any function, right? You give me some function f, I can define its conjugate f star to be, at a point y, to be the maximum over all x of a linear function, right, y transpose x minus f of x. It's a maximum discrepancy between the linear function of x and f of x itself when that linear contrast is formed using y. And we saw this is kind of very intimately related to duality, right? If we think of this as minus the min of f of x minus y transpose x, then this looks kind of like a step we would do in the minimization of the Lagrangian. So we saw it's very related to duality in that sense. Some of its properties, the conjugate was always convex, regardless of the convexity of f. It's a pretty interesting property of the conjugate function. It comes from the fact that it's just a pointwise maximum of convex functions, right, in y. So each of these functions, we might call this g sub x of y. As a function of y, it's just an affine function. So the pointwise max is always convex. When f is a quadratic, we saw, for example, that the conjugate's a quadratic in the inverse quadratic form. We learned that the conjugates of norms are the indicators of their dual norm unit ball. So we learned how to compute conjugates for more than just these two examples. We saw a bunch of examples. And when f is closed and convex, one of the key properties of the conjugate function is that x is a subgradient of the conjugate function evaluated at y, if and only if y is a subgradient of the conjugate of the original function f evaluated at x. So this, we're going to see, is crucial for what we might call dual methods, which is what we're going to learn as an advanced topic. Things like dual decomposition and ADMM. And lastly, if you didn't remember anything at all about conjugates, all you remembered from this lecture was the following, and that would be sufficient. I wouldn't be sufficient. I would be disappointed you didn't remember anything else. But this would be a good thing to remember if all I remember was one thing. That is that if I ask you to take the dual of the following problem, minimize f of x plus g of x, then you can immediately say, the dual is going to be a maximization problem, and it's to maximize the minus conjugate of f at u minus the conjugate of g at minus u. So equivalently, an equivalent dual problem is to minimize f star of u plus g star of minus u. So that's a shortcut to deriving duals if you know conjugates of functions, right? If I told you quadratic plus a norm, you know what the conjugate of those two things are. You know the conjugate of quadratic, you know the conjugate of a norm, so you don't have to actually go through the dual derivation. You can just read it off from something like this. On your homework, you also did something with a linear transformation in there. Okay, now that we've learned duality, we're going to see it kind of appearing everywhere. Things that we maybe, places we wouldn't necessarily expect to see it. So when we talk about the Berry method next week, and then the primal dual interior point methods, obviously, we're going to see duality plays a very fundamental role in those. And we're going to see it a lot in the advanced topics as well. So let's get to the topic of today's lecture. That's Newton's method. And we'll go back to a pretty simple setting, the one that we looked at for gradient descent. And we're going to learn Newton's method in this very simple setting, and then we'll make the setting more complex as the lectures go on. But let's consider unconstrained smooth convex optimization problem, where our function now we're going to assume is twice differentiable. And gradient descent, remember, it chooses some initial point. This is the very first algorithm we learned. It makes a guess, right? That's our initial point. And it repeats the following steps. It looks at the place that we are. That's xk minus 1. It evaluates the gradient of our loss function there. Gradient of f evaluated xk minus 1. And it moves in the direction of the negative gradient, where this tk is a step size. So we repeatedly follow the negative gradient. In comparison, Newton's method, the one we're going to talk about today, it repeats similar steps, but there's a kind of a crucial difference here. Instead of just moving in the direction of the negative gradient by some, along some step size tk, we're going to move in the direction of the negative Hessian inverse of the gradient. So this is gotten by solving a linear system in the Hessian, right? We're going to solve the linear system. The Hessian of f at xk minus 1 times, say, v, we'll call the direction. V equals the gradient of f at xk minus 1. We'll solve for that direction, v, and then we'll move in that direction. Notice that the way I've defined Newton's method here, there's no notion of a step size. It's sometimes called pure Newton's method. We're just taking a full step in that direction. Right, so we solve a linear system like this. Which you might think of as h times v equals g, right, for the Hessian and the gradient vector. And then we'll just update according to xk equals xk minus 1 minus v. All right, so how do we interpret Newton's method? Well, it turns out we can interpret it in a similar fashion to what we did for gradient descent. So remember, gradient descent, we said that, well, at every x, suppose we're at x and we want to make an update. We have our convex function. We said, let's suppose that we form a quadratic approximation to our function at x, which maybe is, say, this guy. In this quadratic approximation, right, this is f of x as a function of y. This is f of x plus the gradient of f of x transpose y minus x plus 1 over 2t times y minus x squared. So that's what this quadratic approximation is. And it's a quadratic approximation where we've taken the Hessian to be the quadratic form of that quadratic approximation to be the identity matrix times 1 over t. That was our interpretation for gradient descent. Once we form this quadratic, we minimize it. That's going to give us some point. Call that point x plus. That point will just be the gradient update, right? It'll just be given by x minus t times the gradient of f of x. What does Newton's method do? Newton's method is something pretty similar, except it uses, in a sense, a better quadratic approximation. It doesn't ignore the fact that our function actually has a Hessian, right? Gradient descent ignores that and just uses the identity matrix times 1 over t as the quadratic form. Newton's method is something different, right? It forms a different quadratic approximation. In a sense, it's better because it's using more information about the function. And it doesn't always have to be providing us with the a longer step, but I'll just draw it that way. This quadratic approximation, let's say, this one is given by the same two constant and linear terms, but the quadratic term uses the actual Hessian. So this is like doing a two-term Taylor expansion of our function. And when we minimize that, it brings us to a different point, right? This point, maybe we'll call it x plus plus or something, which is x minus the inverse Hessian times the gradient. If you minimize this quadratic form over y, you'll see that this is the minimizer. Okay, so that's how we'll interpret Newton's method. So here's a very simple example. I used a pretty similar example for gradient descent, although not quite the same, where I took this two-dimensional function. It's 10x1 squared plus x2 squared over 2. It's a quadratic part. And I added this term, 5 times the log of 1 plus e to the minus x1 minus x2. This part's convex, right, because this is the log sum of exponentials. We know it's convex. And I plotted the contours of that function here in this two-dimensional example. So each one of these lines represents points that achieve the same value under this function. And the function is minimized somewhere in here. Starting out here, I started both gradient descent and I started Newton's method out here. You can see they take pretty different paths to the minimizer. And I hand-tuned them so I tried to have them take the same step lengths. So I just tried to make it so that each one makes about the same amount of progress, just so that you could see the different shapes of their paths to the minimizer. And gradient descent, you can see what is it doing here. Well, actually, let me ask you guys, what do you think? What is it doing here based on this picture? With respect to the contours, what kind of directions does it travel? This is also something that is not just an empirical observation. It's true about gradient descent. Yeah, Dallas. Right, it's moving the direction of the gradient. That's by definition, and that it's also true that that direction is orthogonal to the contour. It forms a normal to the tangent at the contour. Okay, so you can see it's kind of moving in the normal direction along these contours. Newton's method is doing something completely different, and it's actually not a straight line to the minimizer. That may look that way. It's close to that. If I change the initial point somewhere else, you'd see it doesn't necessarily take a straight line path. But it's actually a lot harder to interpret what it's doing with respect to these contours. It's not moving in a direction that's orthogonal to the contours, right? It's doing something very different. The way to interpret what it's doing, one way, is that at every step, it's sphering the problem so that the contours look spherical. That's what it means to do a quadratic approximation in the Hessian. So it's like transforming the space, two-dimensional space, so that locally, at the point where you are, everything is spherical. Then it's taking a gradient step with respect to that new space. It's just following the gradient descent with respect to that new space. And it does that at each step. So here, it respheres the space, so everything looks spherical, and it takes a gradient step. So it's in that new transform space, if we were to plot it, it'd be taking a step orthogonal to the contours in that new transform space. When we look at the original space, it's doing something very different than gradient descent because of the fact that the Hessian here is very far from the identity. And we can see also it seems to take a more direct path, right? Gradient descent has to kind of travel in a somewhat circular fashion because of the fact that the Hessian puts a lot more weight in the first coordinate than the second. So the reason I didn't take the same example, so in the gradient descent lectures, I just took this part as my function. I showed you a bunch of kind of convergence plots to give you some intuition for what gradient descent was doing. I had to add this term, 5 log 1 plus e to the minus x1 minus x2 for this example. Why did I have to add that? Why couldn't I have just minimized f of x with gradient descent in Newton? Yeah, Jersey. Right, yeah. So Newton's method will minimize a quadratic in one step. So that's a fact that you guys should just keep in mind. Right, because in that case, the quadratic expansion that's forming is the original function. So there would be nothing to show there. If you're having trouble seeing that, then just take some time and write out a quadratic and just write out the Newton update. You'll see you get exactly the minimizer of the quadratic. Okay, so here's an outline for what we're going to talk about today. We're going to go through some more interpretations and properties of Newton's method. We'll talk about backtracking line search for Newton's method, which is what we usually refer to as Newton's method. And we usually call the one I just showed you as the pure Newton method. Then we'll talk about some convergence properties of Newton. We'll talk about a version of Newton with equality constraints. And if we have time, I'd like to get to just a little bit on quasi-Newton methods. So what's another way of interpreting the Newton method? So we saw that it minimizes a quadratic expansion that actually uses the Hessian at every step. That's one way of interpreting it. Another way is to, in a sense, linearize the first-order optimality condition, and to think of Newton's method as solving that linearized system. So when we're at x, right, we're seeking some direction v, so that when we take a step in that direction, the gradient is 0, right? Because we're assuming that f is smooth and convex. There are no constraints. This is a characterization for optimality. So we're looking for the direction v that makes the gradient of f at x transpose v equals 0. This is, in general, right, a nonlinear equation in v. Think of x as fixed. It's where we are. We want to find v to make this true. This is going to be a nonlinear equation in v. So we could come up with a linear approximation to this gradient, which is given by a first-order Taylor expansion on the gradient. And what does that look like? Right? That's the gradient of f at x plus the Hessian of f at x times v. This part would be x plus v minus x. It just ends up being v. So this comes from a first-order Taylor expansion, or a linear expansion, like I said, of the gradient equation. And if we were to solve this for v, then this gives us exactly the Newton step, right? The Hessian inverse times the negative Hessian inverse times the gradient. That's what we're telling ourselves that v should be. So this has an interesting historical rule as well. Newton actually originally thought of his method, what we call Newton's method now, not in terms of minimization of some function, but in terms of root finding. So his idea was, if you wanted to find solutions of a nonlinear equation, then that's what he was proposing. And it comes out of this motivation. It's exactly like this. And so we would think of the function, think of one dimension, and think of this function grad f, call it g. We're trying to find the roots of g. That's how Newton's method was originally thought of. And in fact, it was not even for generic functions. It was just for polynomials. So Newton and Raphson both thought of that this idea quite early on. So sometimes you might hear this as the Newton-Raphson method. People in statistics, for example, call Newton's method Newton-Raphson. It wasn't until a while later that people thought about applying this to nonlinear equations. So not just polynomials, but finding the roots of nonlinear equations. And then more generally, using this for minimization by setting the gradient equal to 0. And that's attributed usually to Simpson. So what we call Newton's method now is actually not what Newton originally designed his idea for, his method for. But it's an interesting connection here, right? The idea of linearizing the optimality condition and setting that equal to 0, that's really, it lies at the heart of what Newton was proposing. So one very important property of the Newton step is that it's affine invariant. And we'll make that specific here. Let's just look at a linear transformation. If we looked at an affine one, nothing would change. So let's suppose that you were solving the Newton step in in x, and for some reason I wanted to define a new variable, y, and I'll define it according to x equals ay. Okay, so I'm going to do a Newton step in y instead of doing a Newton step in x. So I'll define the function g of y to be f of ay. Then what does the Newton step on g look like? Right? It's just by definition, it's given by y minus the inverse Hessian times the gradient, this time of g. Suppose, like I said, I'm doing this all with respect to g. Remember that g is f of ay, so the chain rule tells me that the Hessian of g at y is just equal to a transpose the Hessian of f evaluated at ay times a. And the chain rule also tells me that the gradient of g at y is just a transpose the gradient of f at ay. And if I were just to extract the terms here, right, assuming that this linear transformation is invertible, so assume a is invertible, then this just becomes, right, I get a transpose inverse out here. It cancels with this a transpose, and this a becomes a inverse. So I get this Newton step is just y minus a inverse the Hessian of f at ay, inverse this should say gradient of f at ay. Right, so the Newton step just looks like this. And in terms of x, that's exactly, if we were to multiply through by a, right, we'll see that our update on ay looks like this. And if we just recall the relationship between y and x, then we can see that actually this is just the gradient step that we would have taken with respect to x. So if I were to run Newton on x or on y here, which is the relationship between the two of them being that y is equal to a inverse x or x is equal to ay, then it doesn't matter. I would have gotten the same updates, and I would actually have the exact same sequence of iterates if I ran Newton's method. So this means that it's independent of linear scaling. If I were to give you a problem where the Hessian was pretty poorly conditioned, but a linear transformation can make it well conditioned, then in principle it wouldn't matter whether you ran Newton's method on that original space or the transformed space. And the way I see that intuitively came from this explanation I gave you earlier, which is that at every step we're sphering the space to make the contours spherical locally. So it doesn't matter if there's some kind of linear transformation there. We'll always kind of produce the same result. We'll always sphere the space to make everything locally, to make the contours look spherical. Okay, that's not true of gradient descent. Remember we talked about gradient descent depending adversely on the condition number of the Hessian. So even when we looked at the rates for gradient descent, like for example the rate you would have proved, I think it was homework 2. Is that the right? Homework 2 on, you proved a rate for gradient descent in the strongly convex case. We saw there that actually if the condition number was bad, the rate was really bad. That kind of thing shouldn't happen with Newton's method in principle, right? That's what we know from this result. Okay. There's this important quantity now that we're going to define called the Newton decrement. It gives us kind of yet another way to interpret the Newton step, and we're going to see it's also helpful as a stopping criteria and also when we talk about backtracking line search. So this is something that you'll see often when you learn Newton's method. So the Newton decrement, which we usually write as lambda of x, is given by taking the gradient, transpose the inverse Hessian times the gradient, and then taking the square root of that. So lambda squared is just the gradient transpose the Hessian inverse the gradient. And it has a nice relationship to the difference between f and the minimum of its quadratic approximation. Remember, we're forming this quadratic approximation at every step, and f at this minimizer, which we called x plus plus here, and f at the original point x, it relates to the Newton decrement, and that actually the difference between these two ends up just being lambda squared x over 2. So it's the Newton decrement squared over 2. you can think about being defined just in terms of that gap. And how do we see that it actually is equal to what I wrote up here? Well, we can just write it out, right? F of x minus the minimum of its quadratic approximation over all y. This is going to be what we get when we plug in the Newton step. Right? We're going to plug in y equals x minus the Hessian inverse of the gradient. You'll see that just comes out to be f of x minus 1/2 the gradient transpose the inverse Hessian times the gradient. That's because we get a minus 1 times that term from here, and we get a plus 1/2 times that term from here. So overall, we end up just getting a minus 1/2 times that term. And remember, this is just exactly equal to lambda of x squared over 2, by the way we've defined it. So we can think about it as an approximate bound on the suboptimality gap, right? It's not really giving us, according to this calculation, a very rigorous bound on the suboptimality gap. It's not really bounding f of x minus f star. It's really bounding f of x minus the minimum of the quadratic approximation of f. But nonetheless, we can think of it in that fashion, and under certain conditions, I think we might talk about this later. I can't remember if I put on the slides. You can actually use this as a rigorous suboptimality gap. Another interpretation of the Newton direction, of the Newton decrement, right, is that we're looking at the Newton step, which we've written as minus Hessian inverse the gradient, and we're actually looking at the norm of the length of this Newton step, but in a different norm than the L2 norm. It's in a norm defined by the Hessian, right? So what does it mean? The A norm we can think of, right, of a vector. We can think of, for a positive semi-definite A, we can define it like this. You might have seen this in statistics called Mahalanobis distance sometimes. We didn't talk a lot about steepest descent. I think you talked about it a little bit. In steepest descent, we might consider changing gradient descent from basically following, from living in the space of the L2 norm to a norm that's defined in terms of another quadratic form, positive semi-definite quadratic form. And if we were to think about the Newton update direction, which is this one, and we were to look at its norm with respect to a particular quadratic form A, which is just going to be the Hessian itself, then this is going to be the gradient of f of x transpose. So I'm just doing v transpose here, right, which is the inverse Hessian times A being this thing, right, which is just the Hessian, times v, which is, again, the inverse Hessian times the gradient. This whole thing to the 1/2. And you can see that's just exactly equal to the gradient transpose the inverse Hessian times the gradient, the square root of this, which is the Newton decrement. So it's the length of the Newton step as measured by the norm in the Hessian. And that's relevant because, right, we said that the Newton update directions are taken with respect to that Hessian. So if we were to do a local steepest descent with respect to the Hessian, then the Newton decrement measures the length of the Newton step. This is also affine invariant. So just like the Newton updates are themselves affine invariant, this Newton decrement is affine invariant. So you can check that. Right, if I were to define a new coordinate system by some non-singular transformation of x, to take Newton steps in that new coordinate system, then not only the Newton step's the same, but the Newton decrement itself is also the same. The length of each step will also be the same when measured appropriately. Questions? Okay. It turns out that pure Newton's method doesn't necessarily converge. So if we just take pure Newton steps, where we always, we take a step in the full direction of the negative Hessian inverse of the gradient, then depending on where we start, that might diverge. And in fact, we're going to learn that Newton has a very fast kind of convergence rate. So, kind of along with that means that it can diverge very, very fast too. So it can either be really, really good, the pure Newton's method, or really, really bad, depending on where you start. You can see examples of this kind of in very simple settings. So I think on the homework, for example, the very first question of the homework coming up, you'll see in a simple one-dimensional setting, depending on where you start, you can either get Newton's method diverging kind of exponentially fast, or what we call quadratically quickly in optimization terminology, or it converges quadratically fast. So what people always do in practice, I don't think I'm aware of very many things that use pure Newton's method without any kind of type of backtracking at all. People use something like backtracking line search, which is very similar to what we learned in gradient descent. In fact, you can think of them under the same framework too, which is that we'll pick two parameters, alpha and beta, and alpha will be the fraction of decrease that we want to achieve relative to some like linear extrapolation of the function, and beta will be the amount by which we multiply the step size if it doesn't meet that criterion. So common choices are like alpha equals a half, say, and beta equals 0.8, I think we kind of heuristically suggested earlier. And this is the same story that we learned for gradient descent, right? We look at the value of our criterion function if we were to take a step along v once we multiply that by t, and we compare it to something like what we would see if we did a linear extrapolation of our function along this direction. And that's just equal to alpha times t, or that's equal to actually f of x plus t times the gradient of f of x transpose v. And then, like I said, alpha is kind of like a fraction by which we're willing to decrease. We're willing to tolerate some fraction of that improvement because we can't hope to get the same improvement that we would get with a linear direction. And when this condition is met, we choose the step size t. If it's not met, then we make t smaller by a factor of beta. We multiply t by beta t, and we check this again. The only difference between what we learned here and what we learned for gradient descent was that this would look, in gradient descent, you saw this looking like the minus gradient of f of x squared. But remember, for gradient descent, v was equal to the minus gradient. So that's it's really the same as what you're learning here. Now, v is equal to the minus Hessian inverse of the gradient. So you can see where the Newton decrement comes in handy. This is just equal to the minus Newton decrement squared. And when we do backtracking with Newton's method, the nice thing is that we don't have to actually recompute the Newton direction, within each inner loop of the backtracking search. We just compute it once, that's v. And all we're having to do is function evaluations, essentially. So here's an example with logistic regression. So I just wanted to kind of point out that what we get from Newton's method and what we get from gradient descent, they have very different regimes of convergence. They exhibit very different behaviors. So I took a moderate example, wasn't big, with 500 observations and 100 predictor variables, and I tried to solve logistic regression with this setup. And this is not a quadratic, right? So neither method is going to be able to find this in closed form. And I compared gradient descent and Newton's method, both with backtracking. And I tried to make it as favorable as possible for both methods. And what I'm plotting here is the difference between the function at the function we're evaluating at the kth iterate versus its minimum. And we can see that Newton's method, it pretty much converges after something like 7 iterations. And the next blue dot after this is down at like 1 to the minus or 10 to the minus like 20. So I'm not plotting it. So the software tells me that it's too close to 0 and doesn't want to put on a log scale. So basically, it's converged to arbitrarily high accuracy after this point. Gradient descent, it does something different, right? It kind of plods along. It's actually fairly fast here. And it gets down to about 10 to the minus 13 after 65 or 70 iterations. So it's almost like an order of magnitude difference here. This is what we call linear convergence, right? We saw that under favorable scenarios, gradient descent can achieve what we call linear convergence. We call it linear convergence. You can remember that because it looks linear on a log plot. So this is the log of the criterion difference. This is the criterion number. It looks linear. So the dependence here on the step is like something less than 1 to the power of k. So gradient descent converges like c to the power of k, where c is less than 1. This is very different. It's actually not, it's much faster than that. Can any of you guys venture a guess for what the dependence on k looks like here? So this is c to the k for c less than 1. What is this? What are we going to get if we analyze Newton's method? Just a wild guess. C power k squared. That seems reasonable because I called it quadratic earlier. So it's actually not right, though. It's going to blow your mind. It's c to the power of 2 to the power of k. So it's extremely fast. That's what we call quadratic convergence. So we're going to see there's a whole other kind of regime of convergence for Newton's method. What's the caveat here? Why is it unfair to put these on the same x-axis? Yeah. Right. So we have to actually not only compute the Hessian, we have to solve the linear system in the Hessian. Gradient descent didn't have to do that. Let's recall our numerical linear algebra primer lecture. If the Hessian was dense and it was n by n, how expensive is it to solve a linear system in the Hessian? It's how expensive? It's like n cubed operations, right? N cubed flops. This only takes n flops, gradient descent. So the cost of each iteration is actually very different between these two. Something very important to keep in mind. All right, any questions before we get to the actual convergence statement? All right, so just for your information, by the way, how did I get f star? I used, in this example, right, how did I get f star? Because there's no closed form solution, so I would have had to have gotten that from somewhere. I used R's built-in GLM package to compute logistic regression. How does it do that? It actually uses Newton's method. So Newton's method, I think, in some sense, is favorable enough for problems of this size that that's the standard in software for generalized linear models, things like that. So it uses Newton's method. It's maybe a little bit more sophisticated than my implementation here, but they're really the same thing. So let's just, I'm just going to state the convergence result, and then we'll take a break. We'll take a short break after that, and then we'll come back and we'll kind of work through some of the elements of its proof. So let's suppose that f is a convex and twice differentiable function, and we're going to make some fairly strong assumptions about f. We're going to assume that its gradient is Lipschitz with parameter L, and it's strongly convex with parameter M. Remember, these two assumptions right here, the first two assumptions, they are assumptions that we know guarantees gradient descent to have a linear convergence rate. So if the gradient is Lipschitz with parameter L and the function itself is strongly convex with parameter M, then gradient descent is going to converge like c to the power of k for c less than 1. But that c, it depends adversely on the ratio L over M. So the condition number, remember again from homework 1, for example, we know that this is like the largest singular value of the Hessian. This is like the smallest singular value of the Hessian. So the condition number of the Hessian is like L over M. If that's very large, then that c and the gradient descent rate is very close to 1. So it depends adversely on the condition number. So it's linear convergence, but it could be, that c could be so close to 1 we might not be seeing it in some problems. We're going to assume one more thing with Newton's method, which we're going to assume that the Hessian is itself Lipschitz with parameter h. So remember, the Hessian is an operator that goes from Rn to Rn. Right? So it's still okay to define Lipschitzness in this scenario. Just means that actually it goes from Rn to Rn by n. We might just define it like this. Okay, so this Frobenius norm, right? Remember, the Frobenius norm is the sum of the squared entries of this matrix, and then we take the square root. It's just like the L2 norm, but in a matrix space. And in fact, we didn't have to really make this distinction. We could have thought about just unraveling the Hessian to make it one long vector, so it goes from Rn to Rn squared, and then this is just really Lipschitzness between those two Euclidean spaces, Rn squared and Rn. But this is the assumption we're going to make as well. So this isn't actually that important for the analysis of Newton's method. It just makes the analysis cleaner. So we can talk about a different set of assumptions that we can make later as well. So the Newton theorem is a little bit more complex than the gradient descent theorem, but I think it's very interesting. And basically, the result states that if we use Newton's method on a function that satisfies these conditions, and we use backtracking line search with some parameters, alpha and beta, then the resulting iterates satisfy kind of a two-stage convergence result. And those stages are defined by some number k0, which is defined kind of implicitly, but you can think about it as being defined in terms of the problem instance. So there's just some k0 that's going to break up Newton's method into two stages. If k is less than or equal to k0, so if we're in the first stage of convergence, then we don't have a very fast convergence rate. But all we can guarantee is that we decrease the criterion by an amount gamma each time. So initially, we were at f0. After k steps, we'll be at f0 minus lambda k, gamma times k, as long as k is in the first is smaller than or equal to k0, so we're in the first stage of convergence. So it's also a conservative bound here, but we're just saying that we can decrease the criterion by gamma in the first regime, so that the difference between where we are at step k and the optimum is no farther than where we were at step 0 and the optimum minus gamma k. After step k0, so once we enter into the second regime of convergence, we get a very different type of convergence rate, and that's the one it's like the one I was telling you earlier, which is something less than 1, so half to the power of 2 to the power of k. So this k minus k0 plus 1 is just the number of steps that we've taken after, right, k0. So you can think of this as it's something less than 1 half to the power of 2 to the power of number of steps. And this is what we call quadratic convergence. So it converges extremely quickly in this scenario. These constants can actually be made all fairly explicit. So gamma is it's alpha beta squared times eta squared m over L squared. Remember, m is the strongly convex parameter and L is the Lipschitz parameter. So we can see that if the function is poorly conditioned, then it looks to us like gamma should be small. If m over L is small, it looks like gamma itself should be small. So it's basically saying we're not going to be able to decrease the criterion by much in the first stage in every step. And eta also depends on the condition numbers, this time now of the Hessian. It's Lipschitz parameter, its largest singular value, and it looks like this. K0 is defined as the number of steps that we need until we are able to get the 2 norm. This should say, I'm sorry, there's a typo there. So K0 is the number of steps until the gradient at the next step is less than eta. So once that's true, we enter the second regime of convergence. So this is sometimes, by the way, this is sometimes called damped Newton phase and sometimes called the pure Newton phase. All right. Let's just take a quick couple-minute break, and then we're going to plod through the rest of the lecture. We'll go through this result in a little more detail. Let's unravel this result a bit, see how we can understand it. So you can find many proofs of this, by the way. If you want to see a proof with the same assumptions as the one that I wrote down, you look at chapter, I think it's 9, chapter 9 of the Boyd and Vandenberg book. You can see the proof of this. It's actually not very difficult. If you remember our gradient descent proofs, I'd say it's more involved than those, but it's not any more conceptually challenging. It just involves using properties, using equivalences of these conditions, like the ones we learned earlier. But the convergence analysis reveals that a little bit more than the result I told you, and so let's unravel that. And it produces for us two constants, gamma and eta. And gamma is something that's larger than 0. Eta is something that's between 0 and m squared over h. And as we've written them down, these are what they were here, right? You can see they depend on the backtracking parameters alpha and beta. They also depend on the kind of the Lipschitz and strong convexity parameters that we've written down. And it shows that like we said, the convergence of Newton's method follows two phases. The first phase is called the damped phase, and it's defined by the set of iterates for which the gradient of f to the kth iteration has 2 norm larger than eta. And what we can show in that phase is that every Newton step makes progress at least minus gamma. So the difference between f of x k plus 1 and f of x k is less than or equal to minus gamma. Okay, so it's not great, but it's surely something, right? We're proving that actually we have a descent method, and we're descending by at least gamma at each step. The pure Newton phase is kind of an entirely different regime, and we haven't seen this before with first-order methods. It occurs when the gradient of f at, say, iteration k is less than eta. Then we can prove that the backtracking line search always selects t equals 1. So backtracking line search, I'm not sure if I said this out loud, but we're going to start each backtracking task by putting forth the guess t equals 1 and then iterating until this criterion is satisfied. So we'll start off at t equals 1. In the pure Newton phase, we can show that that backtracking always selects t equals 1. So it always quits after the first iteration. There's no decay at all needed in the step size parameter t. We always satisfy that exit condition, no matter what alpha is. And furthermore, we get the following inequality in terms of the gradient. So the gradient at step k plus 1 in L2 norm is less than or equal to, we can rearrange this by saying the gradient is less than or equal to 2m squared over h times the following quantity, h over 2m squared times the gradient at the previous iteration, the norm of the gradient at the previous iteration, squared. So once we enter the pure phase, we know this is less than eta. That actually means that this whole thing is less than eta, right? Because this whole thing is less than or equal to, so we have this squared times this, so we only get one of those, h over 2m squared, times eta squared, right? And so this is less than or equal to just eta, because eta is less than or equal to m squared over h. Actually, it's eta over 2 even, which we know is less than 1. Oops, sorry about that. Sorry, we don't need to know it's less than 1. It's often less than 1 just based on the parameters. This is less than eta. That's the point. So once we enter the pure Newton phase, we won't leave the pure Newton phase. That's what we're saying here. And actually, this is what we call quadratic convergence. It shows us something like the progress is the square of what we saw in the previous iteration. And so, yeah, Sammy.
So, like I'm concerned about the backcutting. Obviously, t equals 1. If I were to imagine this equation, instead of just doing backcutting, I also do a forward search like this, where if that, while the condition is true, I keep increasing my t, so 1, 2, 4 maybe.
Uh-huh.
And the moment it's violated, I stop and do my backcutting on a large t. You get faster convergence and.
That's kind of interesting. So I'll repeat the question. The question was, what happens if we try to take step sizes that are larger than 1 and do something with backtracking where we figure out when it's violated and then go back? I'm not aware of that being done at all. I also don't think that makes a ton of sense because the t equals 1 is actually a very specific. So unlike backtracking and gradient descent, or unlike the step size parameter in gradient descent, the step size t in Newton's method actually has a meaningful scale. T equals 1 means that we're actually taking a step in the quadratic expansion of the Hessian. So if we take t larger than 1, then it's kind of an odd quadratic expansion we're using. For gradient descent, right, the t parameter is like, well, it's really scaled. It depends on the scale of the Hessian, right, because we're approximating the Hessian by I times 1 over t. So I think t equals 1 is really a very natural, has a natural meaning here. I don't know anything about what happens if you take t larger than 1. I don't know if Javier has any thoughts about that. Okay, so we have these two phases that we talked about, the damp phase and the pure Newton phase. We can actually put these results together to get the convergence result you saw on the first page here. That's one way to put these together. It's also more helpful, I think, or it's helpful as well to state them in terms of the number of iterations required to reach a certain level of accuracy epsilon. I think that's a little bit more clear. So let's do that. So if I told you that you wanted to reach a desired level epsilon, so epsilon accuracy, which means that we want to know the number of iterations required to get something like that, then how can we bound the number of iterations required in the first stage? Well, it's fairly simple. Here's a bound the number of iterations required to leave the first stage. Let's just look at f of x naught minus f of x star divided by gamma. Right? This is surely an upper bound for the number of iterations required to leave the first stage, because after this many iterations, if we were to continue decreasing the criterion by an amount gamma at each step, we'd make the difference negative. So that's clearly not possible. So if we're able to achieve a descent of minus gamma, or a descent of gamma on every step, then this is the number of steps required to get the criterion below 0. So it's certainly going to be enough bound steps required to get us out of that first stage. And how about the second stage? Well, so we can actually use the strong convexity, the principle of strong convexity, to get us a bound on the number of iterations required to reach an epsilon level accuracy. Remember, I think that we had something like this. We saw something like this at an earlier lecture. I can't remember if it was the gradient descent lecture or not. That the distance from optimality, we can relate this to, in strong convexity, to, I think it's something like this. We prove this directly from strong convexity. Let's just make sure this is the right direction. So how do we prove such a thing? Maybe it was squared. So let's just figure out how we prove such a thing. So we know that if a function is strongly convex with parameter m, then the following is true. We can get, for any y, we can say that's bigger or equal to f of x plus the following quadratic expansion. It's m over 2 times y minus x squared. Right, now let's take y to be x plus the gradient of f of x, or even x minus the gradient of f of x. And I think what you'll see is that we get a bound of this form. Yeah. So I think I'm not quite reproducing it, but we get a bound of this form from the strong convexity of f. And so what we do when we apply it here is it tells us that the distance that f is away from optimum can be bounded by the gradient of f at our current iterate. And when we unravel that, it looks like log of epsilon, of some constant epsilon naught over epsilon. And so this quantity here that I've written down this is the bound on the number of iterations required to get epsilon level accuracy. So the only step that we didn't connect the dots to was how we get this statement to be realized in terms of a statement in terms of the where we are at step k minus where we are at optimum. But I'm just forgetting some step here. I can put it in the notes after the lecture if you guys are curious to see it. So this is what we call quadratic convergence. You can see the dependence on epsilon is very, very different than we get with linear convergence. With linear convergence, we get log of 1 over epsilon. Right here we get log of 1 over epsilon. That's what this term is called, quadratic convergence. So that's equivalent to saying that this decrease in the criterion after k steps is something less than 1 to the power of 2 to the power of k. It's just flipping it around. I've heard people say the following. It's kind of interesting. How small is log of 1 over epsilon? So what's the very, very smallest you might consider taking epsilon if you were being extremely ambitious? Let's suppose we're doing log base 2. You might take epsilon to be like 2 to the minus 32, right? That's like probably closest to the smallest thing you can store on a computer. Or if you're using long format, 2 to the minus 64 maybe. So that's, what's log of that? It's like 5 or 6. So sometimes I heard people say stuff like, well, yeah, once you enter the quadratic convergence phase, that's 5, or that's 6. And I've even seen that, if you look at the Boyd and Vandenberg textbook, they even write that in there. Just consider that 5 or 6. So it's just going to show you how extremely small this is, this term. There's an important difference in this rate and the ones we've seen already, not only in the fact that this is a quadratically convergent term, but there's another important difference, which is that this is only what we call a local convergence rate. So that means that there's some constant number of iterations here that are required to get us into the quadratically convergent phase. Once we're in that phase, we know we have quadratic convergence, but it's not a global convergence rate. Right? The number of iterations required does not scale kind of entirely in terms of epsilon. We have some constant here. Number of iterations to get us out of the damped phase. So an interesting question is, if I were to set up the results of these if I were to set up a problem with these kind of parameters, gradient if strong is Lipschitz, f is strongly convex, the Hessian is Lipschitz parameter m. We know that the global convergence rate of gradient descent is log of 1 over epsilon. It gets linear convergence. We know that the local convergence of Newton's method is log of 1 over epsilon, so it's a lot faster. You might ask, what's Newton's global convergence? It's way faster than gradient descent when it's in the the pure Newton phase. But what does it do globally? And I believe that an interesting result of Nesterov, a fairly recent one, if I'm not mistaken, says that the global convergence of Newton's method is linear. So globally, we don't actually have much of an advantage over gradient descent in this regime. But locally, we have a huge advantage. And we tend to see in practice is that, you tend to see convergence plots like this, where Newton's method's in the damped phase, And then once it gets to the pure Newton phase, it converges something like that, and then you're at kind of arbitrarily high accuracy for the solutions. But it's hard to characterize this globally. Yeah, Sammy.
Just look at that bound. That bound isn't particularly useful because it's just as bad as linear.
Sorry? This?
I think the custom over there is going to dominate.
Yeah, right. That's why we consider it a local convergence rate. So, I mean, with Newton's method, once you get out of the damped phase, you can achieve as high accuracy as you desire. Going from 10 to the minus 5 to 10 to the minus 20 is a matter of a few iterations in terms of accuracy. That kind of local convergence does not exist with gradient descent.
But my graph is in the bound over here, so it's not saying anything much can compare to. It's not necessarily telling that it's better than gradient descent.
Yeah, I agree. And so what I just mentioned the rate, the global rates being the same, but it behaves very differently. And so in a sense, well, first of all, this is a worst case result, right? So I'm not aware of lower bounds on second order methods, global lower bounds on second order methods. So that's one important point to make. This is like kind of a worst case analysis. And I think it is useful to see, though, the difference in how they behave, right? Because we would use them for different things. With Newton's method, if I'm confident that if I'm looking at the convergence plots and I'm confident that it started decreasing, now that I know that I can basically terminate to whatever level of accuracy I want, that's what this is telling me. With gradient descent, I don't have the same phenomenon. Right? So if you wrote software and you checked when the suppose you're able even to know eta, right, which is not maybe realistic, but we're going to get to a second analysis where things are a little bit more clear. Then if you checked when the gradient was less than eta in terms of its L2 norm, then you can pretty much achieve whatever level of accuracy you want. That's not the same is not true with gradient descent. So I agree. Maybe the rate as written doesn't tell us like that it has an overall strength, but it's a very different type of strength when you compare to first order methods. Okay, this result I think it's a clean formulation of the Newton convergence result. It's also not that hard to prove. I said you can go to chapter 9 of the Boyd and Vandenberg book. But it's actually somewhat dissatisfying, and it's dissatisfying for the following reason. We already proved that Newton's method was affine invariant. Right? We know that Newton's method doesn't depend on like linear transformations. So why do we see stuff like L, M, and H here in the bound? Those shouldn't exist, right? Because if I were to suppose I were to multiply, I change coordinates where I actually, I somehow sphered the Hessian to make it better conditioned, then actually I shouldn't see any difference in the rates. So the final bound should not depend on stuff like the largest or the smallest singular value of the Hessian because of the affine invariance. So it was for a while, I believe, that people had access to results like these, but we're trying to figure out ways to get the bounds not depend on these Lipschitz and strong convexity parameters for the reasons we just said, because they knew that that sharper bounds should exist without those because of the affine invariance principle. And then there was some pretty important work by Nesterov and Nemrovsky about self-concordance. And in some courses, you might go through self-concordance in detail. I think it's a very beautiful subject. It's very interesting mathematically, and in many ways it's very useful. It's a very useful tool for analyzing second-order methods like Newton's method and interior point methods. But I don't think that it's really worth, say, a half a lecture or a full lecture of our time. So I'm just going to give you one slide on self-concordance. If you want to learn more, then the reference that I link at the end, it's this book by Nesterov and Nemrovsky. It's called Interior Point Polynomial Convex Programming or something like that. It's, I think, the definitive reference on self-concordance, or at least it was one of the original references. So self-concordance is kind of an odd notion when you look at its definition. A function that goes from R to R is called self-concordant if its third derivative, an absolute value, is bounded by 2 times its second derivative to the power of 3/2. That's the definition of a self-concordant function. This too is not important. Actually, it would work if any constant was here. And a function on Rn is called self-concordant if, when we project onto every line segment, it's also self-concordant. So for example, the function negative log is self-concordant. You can check that it's, that actually we get an inequality here. The third derivative in absolute value is exactly equal to 2 times its second derivative to the power of 3/2. You can see that because the derivative is 1 over x, right? So when we take further derivatives, we get 1 over x squared and 1 over x cubed, etc. So for self-concordant functions, a very sharp analysis of Newton's method can be made. And it's constant free in the sense that it doesn't depend on stuff like the Lipschitz constant of the gradient or the strong convexity parameter of the function. None of those constants appear. It's a very, very clean bound. And it says that the same story holds. If you use backtracking, then we need at most some constant term, which depends on the distance we were from optimality at the beginning, where this constant only depends on alpha and beta, the backtracking parameters. Has nothing to do with the other constants. Plus log of 1 over epsilon. And I think it was considered a huge achievement in convex analysis and the analysis of second-order methods, the topic of self-concordance. And it's also important for interior point methods. Similar analyses can be performed for interior point methods. An interesting question, which I don't really know the answer to, is, we have a sharper analysis for self-concordant functions, but do we actually get better practical performance of Newton's method for self-concordant functions? And I think the answer is probably no, although I'm not super familiar with people who've looked at that in depth. But from my experience, at least, I think of self-concordance as a very elegant way of mathematically characterizing the convergence of Newton's method, but I don't think it tells us that we actually can do better with self-concordant functions than just doubly smooth functions. Is that fair, you think, Javier, or do you?
Well, the main use of self-concordant functions is for interior point methods for conic programming. So, with respect to disagree, they do have a very strong set of properties that make them lead to then powerful interior point methods for.
Right. So I didn't mean to say they weren't practically important. My claim was that running Newton's method on a self-concordant function versus a doubly smooth function that has the properties we listed, I don't think you would see a big practical difference in the performance of the algorithms, even though we understand the self-concordant rate sharper.
There might be some difference in terms of the local convergence region. So for self-concordant functions, I believe that there are some results about an explicit idea of how close you have to be to the minimum to get into the quadratic convergence. Whereas for any arbitrary convex twice-dimensional function, you do not know that.
Right.
That region of convergence.
Okay. This is probably, this comparison and quasi-Newton methods are probably the most important things, so we're going to focus on those before we quit. So let's do a high-level comparison of Newton's method to the first-order methods we've learned. Very important to keep this kind of stuff in mind. Memory considerations. So each iteration of Newton's method requires n-squared storage, right, if we have a dense Hessian. So we have to actually store the Hessian, and that Hessian is recomputed at every iterate. Each gradient iteration only requires linear storage, right, because all I have to do is store the gradient vector. So if storage is an issue and the Hessian's dense, it's a big difference here. And memory is often an issue for very large problems. Computational considerations. So each iteration requires, we said if the Hessian was dense, on the order of n cubed flops, because we're going to solve a dense n by n linear system, right, to find the Newton direction at each iteration. Each gradient iteration only requires order n flops. That's we're just multiplying the gradient by a constant and adding that to another vector. So there's really not much difficulty there computationally. Backtracking has about the same cost with the two methods. So each inner iteration of backtracking is order n. There's not much difference there. You can see because we've already computed the Newton step before we do backtracking. Conditioning. In principle, Newton's method is not affected by a problem's conditioning, right? If we have any affine transformation is going to leave the steps unchanged. Gradient descent can be seriously affected by conditioning. In fact, the method can degrade if we have a poorly conditioned problem. This one is not as precise as the others, but I'd say there's an issue of fragility we have to pay attention to, or stability, numerical stability, which is that Newton's method, in my experience, is more empirically sensitive to kind of numerical errors, say in the descent, in the calculation of the descent direction. Even if, in principle, it's affine invariant, if you have an extremely poorly conditioned Hessian that's still positive definite, if you go to solve, in software, for the Newton step by solving the linear system, that Newton step can be affected by the poor conditioning just because of the fact that the solvers we use, right, are affected by conditioning themselves. We saw that with the QR and Cholesky, for example. They have different sensitivities, practically speaking. That can lead to an erroneous Newton direction or a noisy Newton direction. I think Newton's method is generally considered less stable or more fragile than gradient descent.
Is there any particular reason you're studying this option duality? Because it seems very close to gradient descent.
I'm sorry, is there any reason we're studying?
You're coming back to these methods after visiting duality?
After duality.
Yeah, because it seems very similar to gradient descent.
So we'll see that duality is kind of the key perspective that we're going to use to understand interior point methods in some sense. And interior point methods are built on top of Newton's method. So there's a hierarchy we'll see next time that kind of makes sense. So here's a comparison of the convergence of gradient descent from Newton's method in that same example I showed you before. But now I'm putting time on the x-axis. This is just, pretty small problem, 500 observations, 100 variables, logistic regression. And instead of the number of iterations taken by each method, I'm putting the time, the total time. So they take different amounts of time, right? Because each gradient step is order p here, each Newton step is order p cubed. And you can see the comparison is less favorable to Newton, although we still do get this quadratically convergence behavior that doesn't exist with the gradient method. Right after about, this is I think only 0.15 seconds, it's a small problem, we're going to converge to arbitrarily high accuracy. So if we wanted the world's most accurate logistic regression solution, we don't have to wait a couple more milliseconds. So we wouldn't have to wait a lot longer. So what's one place in which we might use Newton's method given those considerations? If the Hessian is sparse and structured, and we can solve linear systems in it efficiently and reliably, then that's a place in which we'd want to use Newton's method. So what's another kind of more concrete example? If the Hessian is banded, then both memory and computation for the Newton steps are order n. So puts it on the same scale as gradient descent in terms of that consideration. Right? Because storing that banded matrix is only order n if the bandwidth is constant. Solving systems in banded linear systems we learned was also order n if the bandwidth is constant. So in this particular special class of problems, using Newton's method does not suffer from these kind of memory and computational setbacks, and it's really much more comparable to first-order methods. I put down here two examples of where you might see a structured Hessian. I'm going to skip through these because we have a few more things to get through. But just keep in mind, if the Hessian is sparse and structured, and you have a fast solver for solving linear systems in the Hessian, then you probably should seriously consider using Newton's method. So let's talk about equality constrained Newton's method, and then just a minute on quasi-Newton methods, and then that'll be it. So what happens if we have a problem with equality constraints? So we want to minimize f of x subject to some ax equals b. There's three things we can do, roughly speaking. The first is to eliminate the equality constraints, which is we reparameterize the problem in terms of essentially the null space of A. And we just solve everything in that new parameterization. We already learned this trick at the very start of the class. This is not a bad idea, but it's not always the greatest idea because it requires us, first of all, finding a matrix that spans the null space of A, and also could ruin any structure we had. If we had a sparse Hessian in the original space, once we transform spaces, we could have a non-sparse Hessian. It's very likely we would have a non-sparse Hessian. Another thing we can do is derive the dual. go back to your dual notes, derive the dual of such a problem, you can see that actually the linear equality constraint gets lifted up into the criterion. And we might want to solve the dual. That can work well sometimes. It's not always that simple, right? Because we have to be able to compute the conjugate of f and also some kind of primal dual relationship. So equality constrained Newton is our third option, and in many cases it's the most straightforward one. And so that's a good thing to keep in mind. There's nothing at all complicated about it. All we're going to do is take Newton steps, like we did before, but instead of minimizing the quadratic expansion with respect to the Hessian, we're going to put in a constraint that essentially the Newton step has to respect the equality constraint. So we're going to start off at some x that has ax equals b, and then every Newton step, which we call v, is going to satisfy av equals 0. So we're always going to take Newton steps that let us stay within the constraint region. So all we have to do to find Newton step is to minimize a quadratic subject to an equality constraint. We saw from our KKT lecture that reduces to solving a single linear system. Okay, so I wrote down the linear system here. We solve this linear system in V. That gives us the equality constrained Newton step. And this is often sparse in structure because the sparsity in the structure of the Hessian is preserved, right? And we can do some kind of block decomposition even to solve this in more refined systems. So it's often the simplest. In many cases, it's the most often used for doing equality constrained Newton. I'm going to cover quasi-Newton methods very quickly next time. We don't have time for them now. Let me just mention what we're going to talk about next time. So we've learned how to do Newton's method with equality constraints. How about a general constraint set? What do we do with gradient descent? We did projected gradient descent, right? We learned that if we have constraints, we can project onto the constraint set after every iteration. And a kind of maybe intuitively bizarre fact is that projected Newton doesn't work. So we can't just take Newton steps and then project. Doesn't generically work. We'll see at the end of the class that we can do projected Newton in very special problems as an advanced topic, but it's not a general principle we can use. So we're going to use something called a barrier function that's going to kind of soften the constraints and bring them up into the criterion. And that's going to lead us to interior point methods. So we're going to talk about generally constrained problems, how to solve those with Newton's method next time. Okay, see you on Wednesday.